Hi everyone, my name is Christy Linda Agis Renggoy. Today I'm excited to talk to you about a fascinating and crucial area in modern technology, exploring active noise cancellation. This presentation will cover several key topics. First, I will introduce the basic concept of DSP, then we will dive into the theoretical framework that underpins this technology. Next, we will explore real-life applications. Finally, I will conclude with a summary. Let's get started. DSP involves manipulating digital signals using mathematical algorithms to enhance their quality and performance. In audio, DSP is crucial for improving our auditory experiences, whether it's the music on our smartphones, the clarity of video calls, or the noise cancellation in our headphones. DSP is at work. It filters out unwanted noise, compresses audio files without losing quality, and creates complex sound effects. From recording studio to consumer electronics, DSP in audio processing has to transform how we experience sound. Many applications have emerged in the communication field, but one key element is the transmission signal. Unfortunately, noise and unwanted disturbance often contaminates this signal. Various types of noise like adaptive white, Gaussian noise, shot noise, random noise, and thermal noise can corrupt the original speak signal, leading to communication issues. To tackle this, several methods are available to remove noise interference. One effective approach is adaptive noise cancellation, or ANC. ANC works by adaptively subtracting a reference noise signal from the original noise, effectively reducing the unwanted sound. This method enhances the clarity of the transmitter's signal, ensuring better communication quality. ANC is a method or system that applies an anti-noise waveform at a precise 180-degree out-of-phase angle from the noise at the point where they both reach the target area. The anti-noise waveform closely mimics the shape and frequency of the disturbing noise waveform. ANC systems are typically compact, lightweight, and adaptable to different settings, while some methods are less effective at lower frequency, such as 300 Hz. They can be effective throughout the noise spectrum. The noise source needs to be essentially stationary with respect to the speaker that is generating the anti-noise waveform for an ANC system to be extremely successful. Additionally, for optimal effects, the target noise should mostly be broadcast in one direction, and the ANC system should be situated reasonably close to the source of the noise. ANC systems use two basic methods. The synthesis method, which involves sampling and storing several noise cycles and generating an anti-noise waveform based on the stored information, and adaptive cancellation, which uses one or more microphones to detect noise and then adapts to generate an anti-noise waveform. This is a basic block diagram of an ANC filter. Assume that an input signal is sent and received that has already had noise added to it. An estimate of the sound signal N is obtained from the supply reference noise after filtering using adaptive techniques. To obtain the final denoise signal, subtract this estimated signal from the input. The intended signal from the supply reference noise is ultimately obtained as, which is typically represented as after filtering. To obtain the final denoise signal, subtract this estimate signal from the input. An adaptive filter has two main components, a digital filter with adjustable coefficients and an adaptive algorithm that modifies these coefficients. Several adaptive algorithms exist, such as like this. For noise cancellation efforts, we will focus on using least mean square algorithm. This algorithm adjusts the filter coefficients to minimize noise, and we will explore and compare each parameter to optimize signal denoising. Given that its parameters are always changing to meet performance standards, an adaptive filter is a time-varying filter. The signals are represented by the variables xn, n, and o, and dn, where n is the noise added to the signal, en is the error signal, and dn is the desired signal. The error signal is defined as the difference between the desired and filter output YN. This error signal is sent back to the adaptation process to help it figure out how to update the filter's coefficient correctly. Among all existing adaptive algorithms, the LMS algorithm stands out as the most successful due to its low-cost real-time implementations and low computational complexity. Our proposed noise cancellation method leverages the LMS algorithm to improve audio signals. The LMS algorithm restores the desired signal by passing the noisy speech through an FIR filter, which adjusts its coefficient to minimize the mean square error between the noise and clean signal. This simple design leads to high convergence rate and easy computations. The LMS algorithm simplicity stems from avoiding complex operations like those are in the RLS algorithm, making calculations straightforward. The LMS filter works into two main stages. Filtering process. Here, the filter output and error signal are determined by comparing the output signal to the desired signal. Adaptive process, the filter weights are adjusted based on the error signal. The algorithm can be expressed by the equation. This is the input vector of time delay input values. Wn represents the current filter coefficient. En is the error value and mun is the step size controlling the iteration stability and convergence rate. The performance of LMS-based algorithms is highly dependent on the step size parameter. Larger step size speed up convergence but increase steady state error, while smaller step size improves steady state performance at the cost of slower adaptations. Ideally, the step size should be larger initially and gradually reduced as the algorithm nears the steady state. Through MATLAB experiments, the optimal step size mun is determined under predefined conditions. The filter output is continuously recalculated and the weights are adjusted until the error signal is minimized, ensuring an efficient noise cancellation process. In each scenario, the signal frequency is set to 220 Hz. The result shows the denoise signal result when mun is equal to 0.001. On the other hand, when mun is 0.01, it displays the denoise signal's outcomes. Let's explore real-world application. Typically, ANC is used in devices such as earbuds, headphones, active mufflers, and many more. Now let's look at some examples of headphones that utilize active noise cancellation.
Quiet. ANC on.
In conclusion, the LMS algorithm stands out as a highly effective method for noise reduction in various signal processing applications. Its adaptability to different challenges through the adjustment of the step size parameter ensure optimal performance. The experimental result from this study, especially in the context of speech enhancement, demonstrate that the LMS algorithm can significantly reduce noise, resulting in clearer and more audible signals. Implemented in a MATLAB environment, this approach showcases the practical and powerful capabilities of adaptive techniques in digital signal processing. These are the references that I use. That is all from me. Thank you.